You ever stop and wonder how the ridiculously complex electronics inside your phone or even a satellite actually get designed? Well, it turns out the tools we use to create our modern tech are just as sophisticated as the tech itself. So let's dive into the world of virtual circuit design.
Think about this question for a second. It really gets to the heart of the huge challenge engineers face today. You can't just slap together a multi-million-dollar satellite part, shoot it into orbit, and kind of hope it works. No way. You have to know it's going to work perfectly before a single physical component is ever made. You see, the electronics we all depend on are just crammed with high-frequency, high-speed parts. So the old-school way of doing things, build a physical prototype, test it, find a problem, build another one, that whole process is just way too slow, it's too expensive, and frankly, it's way too risky these days.
And the difference is just staggering. Seriously, look at this. We're talking about shrinking a development timeline from months down to a matter of hours. The cost plummets from thousands in materials and labor to basically the price of a software license. And the big one, the risk of frying expensive hardware, it drops to zero. This isn't just an improvement, it's a whole new way of building things.
So the solution is this new philosophy of design, and it's all powered by software that gives every single engineer their own personal, infinitely powerful virtual laboratory. This is a place where they can build, they can test, and they can perfect their circuits entirely inside a computer.
And that brings us to this core concept, simulation-driven development. Honestly, the best way to think about it is like using software to predict the future. By simulating how a circuit is going to behave under all kinds of conditions, engineers can catch problems and fine-tune performance long before they even think about a physical build.
And one of the top tools that makes all this possible is Keysight's Advanced Design System, or ADS. The analogy here is perfect. It's like a flight simulator, but for electronics. A pilot can practice flying a giant jumbo jet in a hurricane without ever leaving the ground. Well, an engineer can use ADS to test a new smartphone circuit under any electronic condition without ever touching a soldering iron.
So how does this actually work in practice? Let's zoom in a bit and walk through a really simple version of what an engineer does when they sit down to design something in this virtual lab.
It pretty much boils down to 4 main steps. First, you create your project folder. Second, you build the digital blueprint. Third, you tell the software what you want to test. And finally, you run the analysis and see the results. So let's start at the top, step 1. So everything kicks off with what's called the workspace. It's really just the digital box for the whole project. This is where all the different design files, all your component libraries, and your simulation results are going to live. It keeps everything neat and tidy.
Okay, now for the fun part, actually building the schematic. This is the circuit's blueprint. Using a huge library of virtual parts, an engineer can literally just click and drag components, capacitors, inductors, you name it, right onto a canvas and then connect them with virtual wires. Your mouse is pretty much your main construction tool here.
So for our example, let's say we're going to build a simple low-pass filter. This is a super common fundamental circuit in electronics. Its job is really simple. Let the low-frequency signals, kind of like a bass note in a song, pass right on through, while stopping the high-frequency signals, like static or unwanted noise. Now, just building the circuit isn't enough, right? We have to test it. And to do that, we add something called a simulation controller. This is where we lay out the rules for our experiment. We're basically telling ADS, hey, I need you to test this filter's performance across a massive range of frequencies, from 1 gigahertz all the way up to 10 gigahertz. And here is where the magic really happens. We click the Simulate button, and the whole test, analyzing thousands of data points across that huge frequency range, is done in less than 1 second. Just try to imagine how long that would take in a real lab. And boom, you get this perfectly clear performance graph. We can see right away that, just like we planned, signals between 1 and 7 gigahertz are passing through easily. But as the frequency gets higher, the signal gets blocked, or what engineers call attenuated. So, here's the bottom line. It works. We have absolute confirmation that our design does what it's supposed to do. We have super high confidence in this circuit's performance. And we got there entirely in a virtual space. That right there is the power of simulation. But, getting a design that just works is only the beginning. The real power of a virtual lab is the ability to ask, what if, and get answers instantly. This is where engineers can take a pretty good design and turn it into a perfect one.
Just think about it. To change one tiny little capacitor in a physical prototype, you'd have to find the new part, carefully desolder the old one, solder in the new one, and then run all your tests again.
In ADS, it's a double click. You just type in a new value. It's completely effortless.
And ADS is two incredible tools for this. With tuning, you can actually add a little slider to a component's value and watch the performance graph change in real time as you move it around. It gives you this amazing, intuitive feel for how each part affects the whole system. But even more powerful is optimization. You can just tell the software your goals and let it do all the heavy lifting, running thousands of combinations automatically to find the absolute best component values. And here's what one of those optimization goals looks like. An engineer is basically just telling the software, look, in this very specific frequency band, I need the signal to pass through with almost no loss. And at the same time, I need very, very little of that signal to be reflected back. Then they just hit go, and the software goes on a hunt for the perfect design.
So after all this virtual designing and optimizing, where does it all lead? Let's zoom back out and connect these digital blueprints to the actual real-world technologies they make possible.
This technology is literally everywhere. Those complex radio frequency modules in your phone that let you connect to 5G, designed this way. The critical radar and communication systems used in aerospace and defense, you bet they rely on it. Even the high-speed circuits that make your laptop and tablet work are developed using these kinds of simulation tools.
So at the end of the day, here's why it matters so much. Simulation leads to more accurate, more reliable products. It gets those products to market faster, and it does it at a lower cost. And maybe the most important thing of all, by freeing engineers from all that tedious physical work, it gives them more time to innovate and explore brand new ideas.
And believe me, this is just the beginning. As our tech gets even more complex, and it will, the role of simulation is only going to get bigger. The next wave is probably going to be integrating AI and machine learning, letting these tools suggest new designs, predict failures, and optimize systems with even more incredible speed and accuracy.
Which really leads to one final, pretty exciting question. When you remove the physical limits of time, cost, and materials from the design phase, what kind of incredible new things will engineers be able to create when the only real limit left is their own imagination?